So in section 3.1, what we are looking at here is how to use the first derivative to find maxes and mins. And we've had some conversations about this already. You know that to get a max or a min, you take the derivative and set it equal to 0. And there are two locations where a max, a min, or an inflection point. Okay, it's going to be one of three. It can be a maximum, it can be a minimum, it can be an inflection point. We'll talk more about that as we get into section 3.2 and locate it. Okay, that's by taking the first derivative, set it equal to 0. What we had talked about the other day, and I've backed up a little bit here, I think, intentionally. What we had talked about the other day is if you have a function, set it equal to 0, and you get a couple of x values. So let's say we have something like x minus 3 times x plus 2 equals 0. I'm just making something up there in the upper right hand corner, just to use as an example. So if this is our derivative, okay, we don't know what the original function is at this point. I've just made something up, but there's our derivative. This gives us zeros at x equals a negative 2 and at positive 3. Does that make sense to everybody? Now, as we go through this process, and we're going to go through it umpteen times, which is a whole lot more than 10, what you're going to want to do is take the function, compute the derivative, set the derivative equal to 0. Solve for where it equals 0 or for where it's undefined. Okay? One of the things that's kind of nice is that, I mean, this is just a checklist that you go through every single time. You're going to be going through it for the next few months, every single time. Once you get your maxes or your derivatives equal, thank you, your derivatives equal to 0, then what you want to do is to draw yourself out a number line, put down the locations where the derivative is 0 or where it's undefined. Okay? So for that derivative up there, we have two locations where it zeroes out, x equals 3 and x equals negative 2. Then what you do, and we kind of talked about this kind of quickly toward the end of class, what you then do is you pick a value on each of the three intervals. Okay. With those two 0 points, it creates three intervals on our number line. You pick a value in each of those intervals, and you substitute that value into the derivative, because what you want to find out is what's the slope on that interval. Okay, the slope on the entire interval from negative infinity to negative 2 is going to be the same. It's either going to be positive or negative. So for example, on that leftmost interval, what would be a number that we could pick there? It's okay, there are an infinite number of them, you can't go wrong. Okay, something like negative 3, negative 4, negative 5, negative 100, negative 2,638, you get the idea. Pick an easy one, something like negative 3. If we take negative 3 and we substitute it back into this term, actually as factor, we'll have a minus 3 minus 3, which gives us a negative up there, doesn't it? Okay, so what we'll wind up with on the first interval is negative. Pick a number between negative 2 and 3. Make it easy on you. Or wait a minute. If I put in negative 3 here, that's going to be negative. If I put in negative 3 here, it's going to be what? When you multiply everything out. It's going to be positive, isn't it? Because a negative times a negative is a positive. Let's think it down the road too far. Okay, next interval. Pick something like 0, because between negative 2 and positive 3, 0 is an option. If you put in 0, this first factor is going to be negative. The second one's going to be positive, and a negative times a positive is a negative. And notice, am I even concerned about what the actual numbers are? Not concerned. Doesn't matter. All I need to know is the slope positive or negative? Choosing something to the right of 3, that would be something like 4. If I substitute in 4, in the first factor we have 4 minus 3, well that's going to be positive. In the second one we're going to have 4 plus 2 is 6, that's going to be positive. And a positive times a positive is going to be a positive. Okay, so we're going to wind up with the slope greater than 0, less than 0, greater than 0. Does that make sense to everybody? Once you have that, you've got a pretty good idea of what's going on. If the slope is positive, the leftmost interval, the slope is positive. That tells you that on that interval from negative infinity all the way over to negative 2, the function is going up. It's increasing. So what you can then say is, well, gosh, on this interval, the function is increasing. Between negative 2 and positive 3, the slope is negative. If the slope's negative, the function is decreasing. Somewhere or other is our slide. There we go. Decreasing. Then on the rightmost interval, from 3 to infinity, the function always has a positive slope, which means the function is always increasing. With that information alone, you can determine if x equals negative 2 is a max or a min point. If the function goes from increasing to decreasing, you've got a what there? You have a maximum, don't you? That is what is borne out on the second portion of this chart. You will get a relative maximum in locations where the derivative of the sign goes from positive to negative. Anytime you see positive, negative, boom, you know you've just passed a point that's a maximum. For the second portion of this number line, it goes from decreasing to increasing. It goes from negative to positive. It goes from a scenario where the graph's going down to where it's going up. And if you have that kind of behavior, what you now have is a minimum. Now in each case, notice it says relative max or relative minimum. That adjective is important. What that means is, compared to things around it, this is a low point. Compared to things around it, this is a high point. It doesn't mean it is the lowest point possible. It doesn't mean it's the highest point possible. Because you can get graphs that'll do things like this. Where this is a minimum. But is that your absolute minimum? No. Relative to things around it, it's a minimum. This value here is a maximum, but it's not the absolute maximum. Okay? Does that make sense to everybody? So what we have to be careful of is we're going to have situations where we will have multiple maximum values and or multiple minimum values. If we're going after profit, we've got 3 maximums there. Which one do we want? The one that's leftmost, rightmost, or in the middle? Well, I would guess the preferred max or the preferred maximum point for our profit would be there, wouldn't it? Get the highest profit possible. Okay. Okay, so does that make sense on the first derivative? Okay. You can also have situations where when you do your number line, and I'm just going to make up some numbers, -1, +4, and we look at the value of the derivative just as we did previously. Okay, so on the previous slide we did the same scenario, didn't we? But you can get stuff like this, where it's negative, and then it's positive. Where it goes from negative to negative, has it changed directions? Hey there. It's autograph time. Has it changed direction, or is it continuing to head the same direction? If you were skiing or sledding the whole time, do you bike be going downhill? Okay, on that first portion, okay, it's going to be decreasing, decreasing, and then increasing. On this first portion, right there, we have a negative and a negative. So what the behavior is going to be is it's going to be this situation where it's going down, levels off, and goes down. And that point where it levels off there is referred to as a what? That's an inflection point, isn't it? Okay, so what we're going to wind up with is an inflection point. An inflection point makes reference to the fact that the concavity changes. The direction you're headed doesn't change, but the shape headed in that direction changes. To the left here, you can see it's concave up. And on the right portion, you can see it's concave down. So the concavity has changed. Now that's a second derivative issue, but the slope continues to be negative. Tell me what x equals 4 is according to what's written in the upper right corner of that chart. X equals 4 would be a what? Inflection point, relative minimum, relative maximum. Well, let's see. It goes from decreasing to increasing. If it goes from decreasing to increasing, we just passed through a minimum, didn't we? Okay. The left critical value, oh, that's right. We did start using that word the other day. The left critical value is an inflection point in this case. The right critical value is a relative minimum. Does that make sense to everybody? What's going to wind up happening is you're going to be given problems. You're going to compute the derivative, set it equal to 0, find the locations where it's 0 or undefined, draw this number line, evaluate the derivative on each interval, get your increasing, your decreasing, whatever's going on, and then from that, based on what's going on each side of a critical value, determine if that critical value is an inflection point, a relative minimum, or a relative maximum. Okay, that's going to be the name of the game. Math-wise, that's what's going to be happening. Then what we have to do is go back to interpreting so that you can speak to the rest of the world. Okay, you're learning a new language here. Mathanese. And the cool thing about math is if you write this stuff down, you can go anywhere in the world, and anybody else who's studied calculus will know exactly what you are talking about. Okay. I shared with you that story of one of my friends who's down in Costa Rica, right? We're friends now. First time I met him, all he could speak was Spanish, all he could speak was English. Okay? And my wife was working with foreign business execs and was teaching English, and she said, "You'd like this guy, he's really cool, let's all go out to dinner together." So we met him for dinner. And you know those awkward situations where you don't know the person, you're just kind of sitting here and smiling across the table and yeah. And we couldn't even talk. Okay? We couldn't talk. He spoke Spanish, I spoke English, and we were hi. And I could tell he seemed like a cool person. I thought, man, I wish I'd like to get to know this person. But I can't speak to him. Okay? Then he looks at me and says, "Problem." And he pulls out a paper napkin and he writes this problem down that he's working on. He worked as an engineer at Chiquita Banana. Problem. Writes it down. Oh! We burned up who knows how many paper towels, and for the next 2 hours we communicated with each other, and Becky just sat there eating and drinking, and she was completely out of the game. Because now we weren't using English, we weren't using Spanish, we were using math, and we both spoke that language. being taught to do here in part is to be an interpreter from math back to English, or whatever other language you may be skilled in and needing to communicate with people in. Okay? It was great. We've been great friends ever since then. He's learned a little English. I've not done so well learning Spanish. Okay? So, what's going to wind up happening here is when you see this first situation where it goes from negative to negative, you are continuing to decrease. It's an inflection point. The second scenario goes from positive to positive. That's not a maximum. It's an inflection point, once again, on an increasing interval. Does that make sense to everybody? For one moment in time, right there, the function is not increasing. The slope is 0. But otherwise, everywhere along there, it's increasing. Okay. Here's a function. Real fair question Friday would be, graph this, identify the max, mins, and inflection points. Notice I didn't say values, points. A point includes the x as well as the what? Y value. Okay? A critical value only includes the x. A critical point includes x and y. Okay? They mean similar things, but you got to make a difference between them. You got to differentiate. You want something to eat? You want dessert. One's more specific than the other, isn't it? And it brings different options to mind. Same thing with critical value versus critical point. Keep them straight. Okay, so ultimately what we want to do is graph this thing and we want to determine the extreme points. Translation, what's the first step? First step is compute the derivative. When we compute the derivative, we're going to get this 6x squared minus the 6x minus the 12 equals 0. And I'm thinking this should look familiar from the other day, right? Okay. I know we kind of zoomed through it. I wanted to go back through this and make sure it makes good sense to you. It's not that I have Alzheimer's and gosh, he forgets where he was. This stuff's important. We're going to be doing this for the rest of the year. The year being up through April or May. Okay? You cannot divide by an x value. Don't ever do that. Bad, bad, bad. If you divide by an x, what you've done is you've gotten rid of one of your solutions. When you divide by x, you've gotten rid of the option that x can equal 0, which might be your max or your min point. Okay? Remember that these values aren't necessarily always the number of units you're manufacturing. They might be the temperature at which a particular process is taking place. There, 0 is a perfectly good answer. Making 0 microwaves is not a real great answer if you want to keep in business. Okay, so we can divide by 6. We're going to have our x squared minus x minus 2 equals 0. This is going to factor into an x minus 2, an x plus 1. We get 0. This then gives us our number line with critical values at -1 and +2. Does that make sense on those critical values? What you want to do then is to evaluate the derivative on each of the 3 intervals that's reflected here. What we're going to first do is we're going to evaluate the derivative to the left of -1, like -2. If we take our x minus 2 times our x plus 1 and we plug a -2 in to each location, this first factor is going to become negative. The second factor is going to be negative as well. Does that make sense how I'm getting that negative value? So for example, on the second one, what we have is a -2 plus 1. -2 plus 1 is a -1. It's a negative number. I don't care what the number is. I just want the sign. A negative times a negative is a positive. Aha. So on the leftmost interval, the slope is positive. Then we move over to the middle of the three intervals, something between -1 and 2. I'm going to pick 0. Keep life simple. Plug in a 0. Evaluate this first one. We're going to get a -2. It's negative. That's all I care. Evaluate the second one. It's going to be positive. Negative times a positive is a negative, less than 0. Aha. So in the center interval, I assign the slope a negative value. Then we move to the rightmost interval. This gets to be pretty routine, doesn't it? Okay? I'm hoping you're seeing that. I mean, this is just pretty click, click, click. It's just go right down the checklist every time. Is this stuff going to be hard? No, it's just click, click, click. The only thing that'll make it more or less difficult is the actual function involved. Everything else is going to be the same routine every time. Okay? Pick something to the right of 2, so like 3. 3 minus 2 is going to be positive. 3 plus 1 is going to be positive. That means this slope on the rightmost interval is going to be a positive slope. Now that we have each of these three intervals defined as far as the slope, we can come back along and identify, it's increasing, it's decreasing, it's increasing. Notice -1. Is -1 a relative maximum or a relative minimum? It's a max. Yeah, way to go. Thank you. So it's going to be a relative maximum. X equals 2 goes from decreasing to increasing, doesn't it? It's going to be a relative minimum. Now, we have some information about our graph. In fact, we could roughly sketch the graph. I'm going to cheat. I'm going to plug in 0 to the original function. If x is 0, what's the y value? 12. Okay, so if I come up, here's 5, 10, 15. One point on the graph is right there. I don't know where any other points are, do I? Yes, sir. To the left of -1, okay. If you take a look there, the derivative is positive. Okay? So if the derivative is positive, that means the slope is positive. And if the slope's positive, you're going like this, right? You're going up the hill. Okay? Yeah. Check, because sometimes I mess things up. Now, let's think about this for a minute. We've got this point at 0, 12. At -1 is a maximum. If -1 has a maximum, will it be above or below 12? Well, doesn't it have to be above 12 if it's a maximum? Okay, so it's going to be somewhere where, I don't know, it's going to be somewhere up here, but it's going to come up, it's going to come back down. I know it's going through that point. I don't know anything else about the graph except that. And I also know at 2, at x equals 2, what do we hit? A minimum, which means that minimum is going to be above or below that 12. It's got to be below it, doesn't it? So it's going to come down like this somehow or another, and boom, there we go. That is a general shape. The only issue with this graph that I have right now is I don't know what the coordinates are of the maximum point. Neither do I know the coordinates of the minimum point. Okay? It could look like that. It could go like that, couldn't it? Have a lot more amplitude to it. Does that make sense? How do we figure out which of these graphs more accurately reflects the function? Well, how about we get the y value at x equals -1 and then get the y value at x equals 2. Instead of just having critical values, get critical points. So we know that -1 something or other is going to be of interest. 2 something or other is going to be of interest. How do you get the y value? This is where you got to be careful. This is the most frequent mess-up point for folks in this whole process. Uh-oh, he's reaching for his calculator. Where do you get the y value? Do I get it from the derivative? No, the y value comes from the original function, doesn't it? Now, because I got to do it a couple of times, I'm going to go y equals, and guess what I'm going to put into y1? 2x raised to the third minus 3x squared minus 12x plus 12. Okay? So that makes it pretty straightforward to then go to the table function. Oh wow, I got a bunch of stuff in there already. And I'm going to put in -1. Boom. Aha. Gives me a value of 19. Going to plug in 2. Boom. Ah, it gives a value of -8. So realistically, the second graph that I drew that was more extreme in the swings is probably closer to being the real deal, isn't it? Our maximum, okay, and this is going to be an absolute maximum, occurs at -119. Our absolute minimum occurs at 2, -8. Oh no, it ate all of it. There we go. Okay, it didn't eat all of it. Does that make sense? Now be careful, these are critical points. Okay, whereas the critical values are x equals -1 and 2. Don't get those two phrases mixed up. Okay, Friday I'm going to ask, report the critical points. Now if I ask for the critical points, I'm going to want ordered pairs, right? The x value and the y value. If I say, hey, what are the critical values? Just want the x values. And what I'm going to do, either way, I'm going to say, hey, what are the critical points? I'm just going to give a blank line, no hints, no parentheses to remind you that it's an ordered pair. We're just going to do critical values and a blank line, no x equals. Oh, rats, that's mean, Chuck. Why are you doing that? I want to make sure that you know the difference between critical values and critical points. Yeah.
Does the point 0, 12 have any meaning?
Yes, it does. Well, I don't know if it does or not. We'd have to do the second derivative. I was going to jump on board there and say, yes, it's an inflection point, but halfway between -1 and 2 is more like a half. So I'm guessing if there is an inflection point, it's probably at x equals a half.
Where are we going to find the inflection point?
Yeah, how would we find the inflection point? To compute the inflection point, this is fast forwarding to section 2, you take the second derivative and set it equal to 0. Okay, the second derivative gives you if it's concave up or concave down. And where it goes from concave up to concave down, you get a 0. You've got the transition from positive to negative or negative to positive. Okay? So that's what we're going to do in the next section. So that doesn't sound a whole lot worse than this, does it? Okay, so we get some stuff there. There we go. Hey, look at this. There's our graph. You figured it out. See it? We have our maximum here at -119. We have our minimum at 2, -8. And look, here's that point 0, 12 that we were just talking about. Ta-da! There it is. Does that make sense how to do this stuff? You can see better on here that the inflection point is somewhere right around here. Right around there is our inflection point. It's a better graph. Okay. Right around there. Does that make sense to you? This stuff pretty straightforward. Okay, calculate coordinates, there we go, general expression for the derivative. Yep, there it all is. Hey, there's everything we did. Look at there. Everything we did. See it? There's the number line even with the -1 and the 2. Wow, there it all is. Hey, what's this graph going to do? It's asking us what is the derivative. Remember, here we had the derivative is greater than 0. Here we had the derivative is less than 0. And here we had the derivative is greater than 0. Oh, that's what this chart is. Result, it was increasing, it was decreasing, and it was increasing. Oh, wow. All these slides are just that little blurb that we just did. Does that make sense? Hey, this stuff's looking real survivable. There we go. Then we did our first derivative test, get our max and our min. Uh-oh. You do this one. Given that function, graph it and determine the locations of the extreme points, not values, points. And you are very welcome to talk with each other while you're working on this. Then after you've substituted in these values, okay, we've worked through, gotten what x equals, looked at values on each interval. Hey, this one looks just like the last one, doesn't it? Increasing, decreasing, increasing. Something I know for sure is it goes through 0, -6. How'd I get that? I'll just go back to the original function and plug in 0, right? Now it pops -6. So that's a real easy point to pick off, to include on your graph. Okay. So our two critical points are going to be -3, comma, something or other, and +3, comma, something or other. And I'll just jump on. Now be careful when you plug things into the calculator. You got to plug in x raised to the 3rd, subtract 27x, subtract 6. It's real easy to put in the derivative instead of the y value. Okay, it's real easy to put that in, and you'll get some very different values back. In fact, if you plug in a derivative, each of these, where I'm working at critical points, is going to give back a value of 0. To avoid running into trouble, okay, just like I've got this checklist in my head. I hope you realize that and can see it. Geez, he's just rattling down through the same steps every time. Okay, and I'm hoping you'll get this checklist in your head too. In addition to that checklist in my head, I always in y1 put the original function. I always in y2 put the derivative of the function. And in y3, guess what goes in? Where we're headed in section 3.2, the second derivative. I always do it that way. Always. Always. The advantage to that is when you go to the table, it gives you a column for x, and it'll say y1, it'll say y2, and then you can move over to y3. If I'm looking at y3, I always know that value is the second derivative. When I'm looking at the y2 column, I know that that is always the slope. That way you don't have to keep flipping back to y equals, and let's see, which one did I put where? Get things messed up. Okay? You're just starting this. It's a good time to get into that habit. It'll serve you well. There are some habits that are good. Like I always hang my keys on the same hook in the pantry. I walk in the door and the first thing I do is hang my keys on that hook in the pantry. Always. In And guess how many times we have to look for Chuck's car keys? Now, Becky, okay, she's a little bit more free spirit, and her keys are a little bit more set free, and who knows where they are, you know. Okay. Anyway, you get the idea. So, when we graph it, we wind up with a graph that looks like that. That's kind of neat that it wound up almost perfectly aligned with the one where I put things up. That was purely a coincidence. Okay. Does that make sense? So is this graphing stuff that hard to do? Getting your max and mins is pretty straightforward. Okay, here's another one. Go get them. See what you can do with this one. Yes, sir.
When you ask for the relative extreme of the line, will we have to divide the graph?
Okay, if I'm just asking for the relative extreme values or relative extreme points, that just means give me x equals or give me 3 comma whatever it was, negative 18. Okay, if I want the graph, I'll say graph it. Okay, here, find the extreme. Oh man, this follows right up very nicely with what Nick was just asking. Do you have to graph this? Nope. Go get them. See what you can figure out on this one. All right, with this one, we've got a derivative. We've got to negative 1/3 power. Notice I took an extra step and I converted it to a fraction to get away from the negative exponent. Why would I do that here? Well, we're going to take this derivative and set it equal to what? 0. If it's written in the second form, for me, it's a lot easier to think about solving that equal to 0 than having this first form with negative exponents. I don't know about you, but negative exponents and I aren't always on the best of terms. So I try to rewrite it as it would be without negative exponents. Now this is a sneaky point here. Does this equal 0 when x is 2? Well, let's see, if we plug in 2, we're going to get 2 minus 2 is 0. What's the cube root of 0? 0 times 3 is, oh, we'll get 2 over 0. 2 over 0 is 0, right? No, Elizabeth's there looking, no, Chuck, come on. 2 over 0 is what? Undefined, isn't it? Our only critical value here is where the function is undefined. Okay? It's undefined at x equals 2, which means that we have a critical value at x equals 2. We can actually compute the critical point. Well, wait a minute, Chuck. We can't plug 2 in because 2 will give us a 0 in the denominator. That is true. It will give us a zero in the denominator for the derivative, but when we're doing the critical point, we need, oh, that's right, we need the y value. Be careful which function you need to work with. If we plug 2 in for x in the original function, we have 2 minus 2 is 0. What's the 2/3 power of 0? 0. Plus 1. Oh, well, look at that. We really do get a critical point. The critical point is 2, 1. The critical value is 2. Is that a max or a min? Well, you got a 50-50 chance, right? Flip the coin and see what you get. The other thing you could do to determine if it's a max or a min is to say, okay, there's something definitely going on at 2. I'm going to evaluate the derivative on each side of this. If I go to the left of 2, I can pick 0. It's okay to use 0 because if we plug 0 into this derivative, we're going to have in the denominator 0 minus 2. Now, if that was a square root, this would be a problem. You can't do the square root of a negative value, but we're not doing the square root. We're doing the cube root. All I'm concerned about is the sign. I couldn't care less what the number is. What's the cube root of a negative number going to be? Negative. Times 3 is going to be negative. 2 over a negative number is going to be negative. That's all I care about. That's all we need to know. Makes life a lot easier, doesn't it? You don't even need your calculator. To the right of 2, what's the number there? Well, something like 4. Okay. So we'll do 4 minus 2 is now a positive 2. When you take the cube root of a positive 2, you get back a positive number. Okay? I don't know what it is, but it's positive. That positive number times 3 is going to be positive. 2 over a positive is going to be positive. So we go from decreasing to increasing. The point 2, 1 is a max or a min? It's a min. If you graph this, I think I may have a graph laying around here somewhere. Okay, so we got all this stuff. There's 2. Hey, we just did this, didn't we? Remember that chart thing? We just did that. Okay. There's the graph. Notice, remember our critical point that we came up with, 2, 1? Hey, there it is. And notice that this graph is not shaped like an absolute value would be. To the left, that's not a straight line, is it? It curves. To the right, it curves as well. Yeah, I almost shot you with the pointer.
Why is that a relative instead of an absolute?
It's actually both. Okay? Yeah. What's going to wind up happening is, with graphs, you can have things like this. Each of these is a relative minimum. Relative means, compared to things around it, it's lower. There's only one absolute minimum, and it's this one. But is it true that it's also a relative minimum? Yeah. Okay. So it gets 2 titles hung on it. And usually you go with the greater of the 2 titles, absolute minimum. Okay? But it is true that it's also a relative minimum. Does that make sense on that? Is this stuff getting pretty straightforward for you? Okay? One last one. We've got 5 minutes. That's way more than enough time for you to whip through this one. Get the critical points, sketch a graph of it. Critical points and sketch a graph. Now go ahead and I'll start working on it too. Okay so far? Oh yeah, there's that pesky factoring. Yeah. My 4x. Okay. No, you're okay. You're okay. See how mad I get when you question things? And it'll be that way all year. Don't worry about it. Because I am going to make mistakes between now and April. Not on purpose. Let's see. Okay, I'm taking a risk here. I worked out the y values by hand. You may find some mistakes in there. Okay. When you do the intervals, is that what you're getting? Negative, and a positive? Is that working for everybody? Get those right. Uh-oh. Remember I warned you the other day that these things don't always alternate? So take a guess. What do you think this graph looks like based on the information you have there? Well, one thing we know for sure, let's go for partial credit. See that point in the lower right corner? What's that? A max or a min? It's a min, isn't it? So that part of the graph has to go like that, doesn't it? So there's part of it. Tell me about 0, 0. Is that a max or a min, or what is that? It's an inflection point, isn't it? And on both sides of that inflection point, the function is increasing or decreasing? Decreasing. Ah, so we're decreasing. Come in for a landing. Continue down. And ta-da, there you have it. It's just that easy to get the graph. Now this stuff's really cool come Thanksgiving because you can spread your potatoes out on the plate and then with the gravy kind of fill in little troughs and graph functions with gravy and mashed potatoes. Does this make sense to everybody other than the graphing functions and the mashed potato stuff? Okay? You've got enough information now to go after the homework in section 3.1. Okay? And it really is. It's this exact same step-by-step process every time. Get it stored away in your brain. You're going to need it for the rest of the year. Okay? Folks, I hope you have a terrific day. Oh, what's Friday's quiz going to be? Ta-da! This stuff. Okay? Yeah, bring your calculator. I'll see you all Friday.